Okay, this is lesson 3.1. Key definition here is what is a function? A function, by definition, every input has exactly one output. Now, that begs the question, what is input and what is output? Here I have an ordered pair. X is first and Y is second. In an ordered pair, X is your input, Y is your output. Your X values are also called your independent variables, while the Y values are called the dependent variable. X values are also called the domain, and all your Y values are called the range. So, this is the key information. Function, every input has exactly one output. The X value is the input, it's also called the independent variable, and the domain, and the Y is the output, it's also called the dependent variable, and your range. Let's try some problems. Okay, so here I have two tables, and we're going to determine if these tables represent a function. So the first table is for the equation y squared equals x squared. Now remember that this is your input, this is your output, meaning if I put negative 2 into this equation, I would do negative 2 to the second power, which is negative 2 times negative 2. My output is a positive 4. The same thing as we go along here. Now, what you want to do is look to see if each input has exactly one output, and it does. If you put negative 2 in here, you only get 4 out. And the same thing all the way down. Now, an area if we're concerned, because some students get very confused about this, is they would look and they would say, well, look, here 1 is pointing to this one, and 1 is pointing to this negative one, so that's not a function. No, because you're comparing the output then to the input. You have to do it the other way around. Each input has exactly only one output. When you come down here to this one, you have a negative 4 can give you a positive and a negative 3, which means that this input can give you two different outputs. It means it's not a function. So if you see that positive and negative, positive and negative, positive and negative, then it's not a function. This one is a function. If you're explaining why, you would say because each input relates to only one output. Here, an input relates to more than one output, or a member of domain to multiple members of the range, however you want to say it. Okay? Now, some of you are probably wondering how this happens. Let me explain. So here I took the equation that was given to me, and I substituted the first input into the equation. Negative 4 to the second power would give me 16 plus y squared equals 25. Subtract 16 from both sides, I get y squared is equal to 9. Now, how do you solve for a y squared? You do the opposite of squaring, which is a square root. You haven't learned this yet, but this is how you would do it. You take the square root of this side, the square root of this side. This then becomes y, because y times y gives you y squared. And then this, what times itself gives you 9? It would be 3. But it could be a positive 3, because a plus 3 times a plus 3 gives you 9. Or it could be a negative 3, because a negative 3 times a negative 3 also gives you a positive 9. That's how you end up with two possible outputs then. So whenever you have that in there and you're doing a square, that's how. This is also called evaluating the function. If you are putting something in and finding out what you get out of it. Okay. The last thing you need to be able to do is if you look at a sentence and or input to specific inputs and outputs in sentence format and determine whether or not they are a function. So look at the first one, a person's name or identity and that person's birthday. Well, that one is a function because each person has only one birthday. So for this input, yes, you're going to have only one output. This one here, the amount of food eaten and a dog's weight. That one is not going to be a function because you could have dogs, two dogs, say, how about a Great Dane and a Pekingese, and they both eat a cup of food a day. That Great Dane will always weigh more than that Pekingese. You might be a little malnourished, but it'll always weigh more. So you always got to think of the input could have only exactly one output. That's how you would tell. Okay, welcome to lesson 3.2. Here what you're given is a table like you were in 3.1, and you were asked to fill in this and to graph it. Well, it's not a big deal because filling this in is evaluating like you did in lesson 3.1. So what you would do is take negative 2, put it up into here, find out what y would be, and do that for each one of those values. So go. Okay, I filled out the chart. Now what I'm going to do is graph it. So these are your x values, these are your y values. You want to look at this as being an ordered pair. So I have my first ordered pair is negative 2, negative 3. Remember that x is horizontal, y is vertical. So I would go here, say x is negative 2, y is negative 3, and I make a point. Now we do that for the rest of these points. Once I have all of my points plotted, then I will connect them. So this is going to end up being this nice little curve, kind of like this. And again, we put arrows at the end of it. Okay, and that shows our function. Part of this unit also asks you what are appropriate inputs for different types of equations. So here are the real ones that you need to be careful of. When you have a fraction out here, you want to pick a value for x that would be divisible by this denominator. So you could use 4, because 4 over 4 would be 1. You could use 8, because 8 over 4 is 2. What happens is this number should be divisible by this one. And then it makes your other numbers come out nice. You don't have any fractions or any decimals. Down here where we have a root, you want to pick something that would make this a perfect square. So you could put 8 in here, because 8 plus 1 is 9, square root of 9 is 3, and you have no fractions, no decimals. So you want to pick something here that would make the square root, or make this a perfect square. That's really it when it comes to picking wisely. You just want to make it easier on yourself. Also, though, I should point out that when you graph, this goes up to 12 and this goes out to 12 here. So if you pick a value, if I picked a value for x and the value for y turned out to be 30, obviously it doesn't make sense. You never want to extend your graph. Pick different values, maybe go into the negatives or something like that. Okay, lesson 3.3. This is, first of all, you need to determine whether a graph is linear or nonlinear. Well, look at the word itself. Linear, if you get rid of this, you have the word line. In other words, does it form a straight line? If it does, then it's linear. Here's an equation, y is equal to 3x plus 2, and here's the graph that's associated with it. You see it's a straight line, so this is linear. Here's kind of a quick trick that I want to show you really quick when it comes to equations. If you look at the exponents here, the exponent on y and the exponent on x are both 1, this is going to be linear. It's going to be straight. If this is squared, or if you have 3 and it's raised to the x, or if you have square root, plus x, or 3 times x, and there's a square root involved, it's not going to be linear. So, exponent is 1, linear, and if it's not, it's going to be nonlinear. Now, something else I want to point out to you. This right here is called a slope. This right here is called the intercept, the y-intercept. Okay? How that is helpful is when graphing this equation. You can graph really quickly. Check this out. This is where, if it's in this format, this is called the y equals mx plus b format, where the b, this number, is your y-intercept. The m, which is the number in front of the x, is your slope. This is where the graph will cross the y-axis, so at 2. And then the slope is the rate of change of the line. So it's 3. We need it as a fraction, it's 3 over 1, which means you go up 3 over 1, up 3 over 1, or down 3, back 1, down 3, back 1, and the line goes like this. Pretty cool, huh? There'll be more about that later, so don't worry about this so much, but this is something that I thought I'd introduce to you kind of early. The next thing I want to show you is when you have a table, if you want to determine whether or not it is linear, and you don't feel like graphing it, maybe you don't have graph paper with you, what you can do is you can look at your y values, your output. If the output goes up by the same amount each time, then this is linear. So example, go from here to here, what you're doing is you're adding 2, going to this side. Then to go from 1 to 3, you add 2. 3 to 5, you add 2. 5 to 7, you add 2. Each time you're adding 2, which means the y value, the output, the range is going up by the same amount each time, so it would be linear. What if you were given a blank table and it said, come up with numbers that would show a linear relationship? Don't freak out. The easiest one in the world is this, y equals x. So in other words, x is 1, y is 1. 2, 3, 4, 5, 2, 3, 4, 5. Done, right? Each time, what does it go up by? It goes up by 1. We know it's linear. It's y equals x. That would be right here. Because every time you go to 1, 1, or 2, 2, 3, 3. And it would be a 45-degree angle going through the origin. Great, lesson 3.4. In this one, you are going to be given boxes like this, and you're going to be asked these questions here based on a story problem and an equation, and you're going to have to see what it means. So notice what we're trying to find out is, do you really understand what all these things are and how it relates to the equation? So here I have a rocket's distance traveled in meters, which is given by d. I don't know why d, probably for distance. Based on the time in seconds, t is measured by the following function. Distance is equal to 5 times your t in seconds plus 2. And here I said, what is the conceptual description of the rate of change? Remember that whole y equals mx plus b thing that I talked about earlier really briefly? Your rate of change is this, okay? And the initial value is this, your y-intercept. So if you were to graph it, this is your initial value. That's where it crosses the y-axis, and here is your rate of change. So look in here, this is my rate of change. And what does that mean? Well, we're talking about distance in meters, so that means that it's 5 meters, and it's in seconds per second. So 5 meters per second. That's what that means in this particular problem. That is also our rate of change. So 5 meters per second. 5 meters in 1 second. Okay? The initial value, well, I already said that's this right here. That is 2. But what does that mean exactly for this problem? That means that since we're talking about how far this rocket travels in a certain amount of time, but we're saying it's already 2 what? You're talking distance, 2 meters off the ground. So in other words, before it ever took off, it was already 2 meters off the ground. So it's 2 meters off ground before it took off. Okay, that's what it means. Probably like the platform or something that it stood on. Now, independent and dependent, you got to remember that your x value and your y value, your x value is always your independent variable. So independent is going to be t, because we just said it's t instead, and your dependent is y. And again, this is because this depends on whatever you put in for x. So or for t in this case, if I put 5 in for here, it'll give me a different value for this. This one always depends on that one. That's really what this comes down to. These are thinking problems, so it's going to take you a little bit to get through them. Here's the exact same problem in a graph, okay? If you, again, your x value is here, and then your y value is here. This right here in that y equals mx plus b, that's the initial value. That's where it crosses the y-axis. So if you're given it in a graph and you want to try and find it, you go to this point here where it crosses the y-axis. At y equals 2, or in this case, it would be d equals 2, and the distance is meters, so we would say it started 2 meters off the ground and it took off, okay? But again, it's where it crosses that axis is the initial value. Okay, sometimes you are going to be given a problem like this, and you're not going to be given the equation, but you're still going to be expected to find all these different things, your rate of change, your initial value, your dependent, your independent variable. So here, this problem is saying, all right, let me read it to you first. It costs $5.50 to mail a large package to New Zealand. Okay, so no matter what, it's going to cost $5.50. The post office will weigh your package and charge you an extra 30 cents per pound. So in other words, this is how much it's going to cost to send it no matter what, and then also 30 cents per pound. Think of a linear function that demonstrates the cost to mail a large package to New Zealand, and they want you to use c for the cost, based on the number of pounds it weighs, p. So you have to come up with an equation. The best thing to do, that's what it's asking you when it says, right here, think of a linear function. They're saying write an equation for it. And then you can identify all the parts. So let's identify, first of all, what are the independent and dependent variables? That's something you need to think about. Let's say this was my large package. I know it's a piece of paper. And I wanted to send this thing. No matter what, this thing is going to cost me $5.50. So I know I have to use that number. But cost really depends on how much this thing weighs. If it weighs 100 pounds, well then they're going to charge me 100 times 30 cents. If it weighs 10 pounds, they're going to do 10 pounds times 30 cents. So the cost is the dependent variable, or the y, and the weight is the independent variable, or the x. Remember this, that y equals mx plus b. That's our linear function, where this is our rate of change, and then this is our intercept, and here is my independent, there is my dependent. Well, let me replace what I have. Well, first of all, I'm going to say P. I'm going to erase this right here. There's my independent. C. There's my dependent. Now the question is, what are these things? Well, remember that I'm going to take 30 cents times the number of pounds. So that has to go right here, m times that. That's my rate of change. My slope, 0.3 times p for the weight. And then what is the b? That's the initial value. That's how much you're going to be charged no matter what. Right here. So that would be the equation. The cost would be equal to 30 cents times the weight plus the $5.50 charge. Now, can we pull out all the other questions? Okay, so here are the things that you want to be able to point out from this equation. So first of all, the rate of change. Well, again, that's your slope. That's right here. That is equal to 0.3. The initial value, that would be this number out here, your y-intercept, or 5.50. Your independent variable is your x, or in this case, the p. So it would be p, and your dependent then would be the cost, c. Now there's also these two lovely boxes over here. It says the contextual description of the rate of change. So in other words, what does that exactly mean? Well, that means that it's 30 cents per pound to send the item. And then there's also the contextual description of initial value. And what does that mean then? That means that if this thing weighed nothing, 3 times 0, and you were sending it, it's still going to cost you $5.50. Although technically, I don't know how you can send a box that doesn't weigh anything, because it's always going to weigh something. Okay, lesson 3.5 is all about identifying an increasing, a decreasing, and a constant function. So, in increasing, now when we look at a graph, we always look at the graph from left to right. So I'm looking here, and as we go from left to right, this one is going up, which means it's increasing. From left to right, this one is going down, so it's decreasing. And this one is horizontal, left to right, so it is constant. Now, there's a certain way you can identify them too in an equation, and I'm going to write those and show that to you. Here I have 3 equations that show increasing, decreasing, and constant. Try and see what the difference is. Really quick. Okay, this one is exactly the same as this one, except for this right here, the slope. Remember that y equals mx plus b I talked about before? This right here is your rate of change. See, this one's a positive number, this one's a negative number. That means that this one is increasing, this one's decreasing. Down here, there is no rate of change. There is no variable, or no x variable, so there's no rate of change. In other words, y is always -3. In fact, that's this one here. No matter where we go on the x, the y is always a -3. This is a representative constant. Decreasing, increasing. The last thing that we need to talk about for 3.5 is the idea of maximum and minimum. It's just exactly what you would think. If you have a graph like this, there is a point right here where you would have the maximum value for y. If the graph was the other way around, like a smiley face, then you would have a minimum point. So here at, let's see, this is about 1, 2, 3, x equals 4. You have a maximum y value of 1, 2, 3, 4, 5. So you would say that the max is y equals 5. And then that happens at x is at 4. Same thing if it was flipped around, except it would be a minimum and it wouldn't be a maximum. This one has no minimum because the graph goes on forever. But if you see a point where it curves like this, and it goes back down the other direction, that's a maximum, or if it's going the other way, that would be a minimum. Sometimes you have a graph that looks like this. Well, now you say, well, what's the maximum, what's the minimum? And you wouldn't necessarily just use those words, you would use local max and local minimum. What this means is it's local. In other words, it's not the maximum point for the entire graph, but it is for this particular area, or this particular region. So at x is -4, we have a local max of 4. And then over here at x is 2, we have a local minimum of y is -4. So here it would be y is 4 and y is -4. And again, because it doesn't represent the whole graph, it's not like it was like this. You can say, oh, well, that's the max, or like this, and that's the minimum for the whole thing, because it goes like this. So it's a local minimum and local maximum. Okay, lesson 3.6. So this one, what they're asking is, if I have a graph here, can you interpret it? Can you tell me what this really means? So this is one that was from the notes. And the first question they would ask is, what inputs make sense for this graph? Well, remember that your inputs are your x value, which is your domain, which is your independent. And if you look, it would only make sense here from -80 to 220, because beyond that, the bacteria, because this is what it's measuring, bacteria wouldn't live. It would be below 0, so only in this range would it make sense. Oh, I shouldn't use the word range, use domain. Anyway, the next one, what are all the possible population sizes? Well, you could have nothing, You got to look at, now see, this is temperature, this one is population. You could have nothing all the way up to, it looks like about 260, and this is in millions, 260 million. And then what is the highest one? That, well, the highest is going to be the max, which is here and here, is 260 million. And then, let's see, what is the next question? What temperatures give the highest population? Well, here you have the population peaks at two different points. So you would go down and look at your graph here and get the two temperatures, which it would be the highest. And it looks like it's about negative 32 and about 170, something like that is for those. And then the lowest population, let's see. Here, let me put this down. I'm going to turn away from the camera. All right, what is the lowest population that they could be in comfortable living temperatures? Well, that's a little open to debate. For me, comfortable living temperature is 80 degrees. But if you see, this is the low point right here, a local minimum. And this is right around a comfortable living temperature. It was about 70 degrees or so, 65, something like that. And then it says, at what point are there bigger and bigger populations, and at what point are there smaller, smaller populations? Well, that has to do with the rate of growth. Remember that we always look from left to right. So as it's increasing here, that's where you would have your biggest. As it's increasing here, that would be the biggest growth. Going down here would be your decline or the decrease, and the same thing here. It's just, can you look at this and make sense of it? That's what this whole section is about. Okay, lesson 3.7, a piecewise function, or sketching a piecewise function. What that means is you're doing it in pieces, and you're putting it together, and you could end up looking linear, and then curved, and all kinds of different things, depending on this particular problem. Now, there's not an exact science here, but here, I want to show you an example from your notes. This is George was at a friend's house, and he began walking home. So, all right, let's just say a distance. So here's his house, and he's a certain distance from his house, okay? And he begins walking home. So what he's doing is he's getting closer and closer and closer and closer to his house. And then, after a few blocks, he realized he forgot his cell phone and hurried back to his friend's house to pick it up. So he hurried back to his friend's. That means he went faster, but the distance is still going to be where his friend's house was, okay? And then, after grabbing his phone, he immediately began running back home because he was afraid he was going to be late. Okay, so he's running back home. Now he's going fast, right? But I'm going to stop right there because next it says, unfortunately, he got stuck for a little while crossing a busy street. So he goes, and then all of a sudden, he's stuck. Time is going by, but there's no change in distance. It's still the same, okay? And then, after crossing the busy street, he decided to walk the rest of the way home instead of running. So here is the rate. It's very fast. Now he's walking, and it's a much slower rate than it was before. And that would be a graph, and it's put together in pieces. Looks a little different, but it represents a story problem, and that's essentially what you're doing. Okay, now for the review. On this test, you are going to have to you're going to have two tables, and you're going to have to tell me whether or not they form a function. So you have a table like this. Here's your x, here's your y. And say 1, 2, you have 1, 2. Is this a function? Yes, it is. Why? Because each input has exactly one output. When you have this thing, then it's not, because each input goes to more than one output. It's as simple as that. You're going to have some word problems where you're going to have, you're comparing one thing to another. You want the same thing. Could that input have multiple outputs? So, for example, if I said 12-year-olds are 70 inches tall, and is that true? Well, no, it's not, because 12-year-olds could have you could have different heights. So you're not one particular thing. So you got to think about it in the context of the problem. Next, you are going to be given some equations, and you have to determine if they are linear or not linear. So, if you have, my markers are dying on me. If you have the exponents here are both 1, and there's no roots, it's linear. The minute you do something like this, or you put your exponent up there, or you do that, or you do a root around the whole thing, then it's not linear. Okay? If it's just the power of 1 on each one of those, or the exponent is 1 on each one of those, then it's going to be linear. Then you're going to be given some tables, or an equation I should say, and you want to graph them. The way you do that is you fill out the table. The only thing you have to be careful of there is if you're given a root, like this, you pick numbers for x that'll give you a perfect square there, so that your numbers for y turn out to be whole numbers rather than decimals. Here, you would pick something, if you have a fraction, something that would be divisible by 3, so when you multiply, the fraction goes away. Next, you're going to be given a couple of problems where you have to determine the rate of change, the initial value, the dependent variable, and the independent variable. Tell contextually what does the rate of change mean and what does the initial value mean. So if you were given an equation, which you may be and you may not be, but let's say you were given one. Right here, this is your initial value. Right here is your rate of change, or your slope. So when you were trying to identify them, there they are. If you were asked to find out the independent and dependent here, well, the independent's x, the dependent's y. However, in a problem like on the test or on any other worksheet, it would probably be something more like this, C, T, and it would say which one is independent. Well, T, the one that's over here. The one that's dependent here depends on what you put in there. Okay? And then what does it mean? Well, for the particular problem, this is your rate of change. So how much something costs, something like that. This initial value, what does that mean? Well, if there is a cost, maybe that's just the initial value, like the box problem that I talked about before. It could also mean if you're starting at, if you have 0 here as your first number, that could just mean that there's no cost. There's no initial cost. If you're mailing a package, for example, and it was like this, and it was cost, and then say pounds, okay? So I think it was 3p or 0.3p in that one problem, right? 0.3 times p. What this would mean is that cost is still dependent on how much it weighs, but there's no initial charge. That one had $5.50, I think it was from before, right? So this one, there's no charge. That means there's no cost for mailing something that doesn't weigh anything, which would make sense. Okay, then you're going to have to solve one of these, though, that is in word problem format and does not have the equation. So for there, remember to first identify what is independent, what is dependent, and then you could put an equation for it, where y equals mx plus b. Got to remember that. Y equals, this is a horrible marker, I'm so sorry, and equals mx plus b. Here is your rate of change. Here is your independent variable. Here is your dependent, and there is your initial amount, or your y-intercept. And then you're going to be asked to graph an equation. Actually, the equations will be graphed for you and tell whether it's increasing, decreasing, or constant. And then you're going to be asked to draw one that is increasing, decreasing, or constant. So increasing obviously goes up from left to right, decreasing down from left to right, and constant is just horizontal. Okay? That's it. Have a great day.